I've sent the link to you all, which is directly going to a binder. So where does this come from? This binder is now our little go through for today. And it's from the package Fall in Love with Julia, which you all have seen linked on the meetup invite. And there you see also the link. So this is like every time in the sessions you have your own Jupyter notebook with which you can work, and clicking this launch binder here, you will come to an overview where all the notebooks are in. So if you want to check out one of the earlier sessions, just feel free, take a look at them. I provided this link now, which gets you directly to the machine learning with Julia part. I make it a bit bigger, a bit larger for us now. Yeah, so this is where we're going to go through. So every one of you should kind of have this little environment, and then we are ready to go. So thank you all for joining today. Machine learning in Julia is the topic, and I want to present to you the package MLJ. So that's the standard package in Julia to just get some work done. And you can think of it like in R, there's MLR or caret, and in Python, there's scikit-learn. And it's really one of these meta packages which summarizes and brings together a lot of machine learning models. And bringing together these models, one key part of it is really also composing these models. And we're going to see that MLJ is coming with some extra functionality for this. That's really nice. So please always feel free to ask questions. I'm seeing the chat, I'm hearing you well, so this all works fine. And just come along, try it out. One last remark in case your session breaks, just get the link again, because it may be if you haven't executed code for, let's say, 15 minutes or something, this free environment provided by you by the binder community, supported by Google and Turing and others, may actually then be shut down because of you haven't used it, and then you need to restart it. But no real problem. Just again click on the link and you will get it fresh. So the first thing I want to note is that you can go to the GitHub page. So I just posted it in here. I copied it in here, and you can see that this package is really well founded. And I myself, for me, it's always important to have packages which are really kind of profound. And this one, has a strong backing of multiple organizations. So many universities with a lot of funding, and also proprietary companies. And the second point here, which thanks for reposting, Jose, the GitHub link also. I just see the first questions already. Sorry for jumping here. So are there any video audio recordings from your previous sessions? There are, and I'm just a bit too lazy. They are not yet online. Thanks for pushing. It's always good. It's just that I'm also doing this free time, but I'm going to improve myself and make this a regular thing. So because the recording worked, and I'm going to push it to YouTube then with support from Julia. But very, very good question. And same for this one. So this is from the GitHub main README page. So this is just to see that this is a whole ecosystem. So this is more a thing which gets together many components, and they are well organized in an extra umbrella organization, the Julia AI organization. And there you have a lot of packages, MLJ ensembles, MLJ OpenML, and many other things which are there for plugging things together, and of course for providing the core functionalities. So this thing is really well supported, and also meant for being extended in the future and being the go-to package where everything is glued together for machine learning purposes. Okay, so I see a little thing from my side. So this first line is not needed. You can delete it. This was just for my local testing. I'm sorry for having not spotted that one. So the first line we're going to execute is that we use this MLJ package. And yeah, to get you in here, I decided to now directly work with the package so that you see what it is for and what it can do. Yeah, one point is that we now use some Julia syntax, and as this is still a 101, but I guess a couple of you have been in previous sessions, I'm only getting a few things. So you probably used R or Python at least, and so things are a bit similar. This thing here, however, is a bit special. This add thing, this is called a Julia macro, and it's really nothing dangerous. It just has the power of rewriting the syntax what you wrote here. So a really good example to see what it means to be a macro is just to define a couple of things. So I just had here a new cell, x equals 1, and now I can use a little macro which is called show, and it will print x equals 1. And this is not possible by a simple function because this is the name of the variable. And we have a little helper which is called macro expand, and this is in this case very sorry, I had a bit too much. You see that it does restructure the code and does print it and gets kind of the name from it and then the value. And this wouldn't be possible by a simple function. So if you use the printer, just yeah, it will print 1, but it has no information about what was actually the name of the variable you used. So in this, I think, is a good little thing to understand what this is. And yeah, it's just sometimes it's more convenient to be able to change the syntax in addition to execute functions. Okay, so what do we do here? So if you execute this one, you actually get a command line where we can type things in. So we have here the standard in, and I can really type things here. And the package is speaking with me. And yeah, so we are loading now a classifier, the decision tree classifier. However, it mentions that there are actually 2 different classifiers in there. And the decision tree version, so there are 2 different packages which implement them, this decision tree and better ML. I take the first one because I already installed it in the environment, so it should load faster. But in principle, you can also take the second one. And yeah, and it will import it, and it's nice. There's another macro for it without the I in front, so simple load macro. And here you have to specify the package explicitly if there's an ambiguity. And yeah, and this works too. But it's really nice to have this interactive version, just so that you don't have to care so much about where the package is, and it will all be provided by you. So that's handy to know for starters. So I really like that. So what do we have here now? We have our now a type, which is summarizing our decision tree classifier, which we want to use for some machine learning, and we now get an instance from it, which we just call tree. So again, we use simple assignment, and we call this this type. So we construct it and get an instance of it. So I hope so far that was simple to go. In case you have questions, please always raise, or also simple questions are welcome. I'm happy to explain anything I can. Yeah, so first remark, and this is actually a good memorization. So this MLJ package is actually like a big wrapper around all these different models. So the MLJ package itself does not come with concrete machine learning models, but it just has a registry, if you want, where all these things point to. And we see a bit later what this registry is concretely about. But this is a good memorization. So this is really just a point where everything comes together. So let's do some stuff. And we first load some data. So we use the package R data sets here. And you see, so we have now the import name here. So import, and before we saw the using. The using is like an import, but in addition, it gives you access to a couple of variables or functions. It's similar to the R library function, which not only gives you access to the package, but also loads a couple of things into your current namespace. So the import does not do it here in Julia, but the using does it. Hence, we already had this load and so far. But if we only use the import, we have to prefix all our functions with the name of the package. So hence, we do here r_dataset, stop dataset, and have the famous iris dataset. So a little helper function here from MLJ, which provides us a simple way to extract the target variable y, which is the species, and all the other columns, the covariates. There's a pretty printer here, which you can use to also visualize the data. That's nice. And if you want to get a bit more information about how this little unpack function works, remember, or it's good to know, if you use the question mark in front of a name, you always get the documentation here. And things are usually quite well documented in Julia. So here you have the unpack function. And there's actually a nice typo. So if you want to make your first pull request to the package, that would be a nice thing to fix. So this is always welcome to fix these little things. I don't go into more detail into this little helper. Thing is, we now have our training data. And maybe to take a better look. So to see what we have here. So we looked at X, and you see that there's no species in here. So X is really only containing our training columns, our covariates. And if we take a look at Y, so then we see that this is really just a vector categorical array, a special thing of Setosa and all these species names. So if we take a look what species names there are, so we can experiment with this like normal Julia. There are only 3 species names: the Setosa, versicolor, and virginica. So standard Julia stuff. Of course, as always, you have to know a bit these methods. But you can also Google it and find answers, like what things do what. So, and you get familiar with these things because you use them all the time. So let's go into the machine learning part so that you see that this is really like scikit-learn. There's one extra step in the beginning, and we'll see later on, I hope you have time for that, why this is actually a key component of the package. So we first wrap our little tree model with the data, which is our covariates and our target. So this is all the information which we need to train the tree. And and this is combined then with the cache, actually. So for performance reasons, some results are stored internally, including the training parameters. So if we train it, then of course we learn the parameters, and these are also stored in this machine. And this is actually the term MLJ uses everywhere. So if you have something which is trainable, then this is a machine. Okay, so a simple application now is to just train it on some train data and test it on some test data. You're probably familiar with it. And the way we do this is that we do a split. And we don't split the data directly, but we split the indices of the data. So each index is now giving us let's construct a machine, giving us an array from 1 to the length of y. So actually, it's a bit condensed even. And we take the first 70% to be the train and the other 30% to be the test. And so that everyone has kind of the same thing, we do a shuffle here. Turns out that by testing it, not everyone has the same thing here for sure. I already raised an issue to MLJ why there's some randomness left. Let's see what they answer, but they haven't answered yet. Okay, so we have this partitioning, and now you can also take a look at them. So if you ask yourself how I add all these extra cells here, so there's also a little button here on the top. The plus will add a cell, and you can also cut cells to delete them. And yeah, and there are some shortcuts to it. If you know them, that's a bit faster. You see they are just vectors from 1 to 105, and test is then from 106 to 150. So really the thing which we expected. And now we can fit our machine on the training routes by using this syntax. So this is also indeed kind of intended syntax. So we have a generic machine which knows all its dependencies. And now fitting it, we can specify which concrete data it should choose. It should train itself on. And there's this special syntax rouse, which just expects indices instead of data and uses the original data. Okay, and then we have the second method, which is called predict. So really like the standard function names. We again have the machine, which is now trained, and we use standard index syntax to get only the test data from our X. So this is indexing into the rows, and this is taking all the columns. So first dimension and second dimension. I hope this was not wrong. Okay, and then we have our predictions, which we here call y hat. And just that you see what this actually outputs, I print from 3 to 5 a couple of examples. So as always, please feel motivated to go through these examples with us. Okay, does partition returns a dictionary? Thank you so much, Jose, for asking the question. No, partition actually returns, that's a good question, returns a tuple probably. Let's take a look. And it might return a named tuple. So with the type of function, you get the information, but no, it does not name its outputs. Yeah, because it would just be a convention. So yeah, it's just a tuple. And I index by test because I saved this tuple into 2 variables by auto-expanding it. So this is Julia syntax similar to Python. So you can do this. So you can destruct a tuple into 2 variable names, and yeah, you don't have to write the parentheses. So that's really the same. And hence I got these 2 values here and stored the first one on train and the second one on test. And really they are indices, and this works. So they are integer, and this is the first row, second row, 3. Yeah, and this way you can index into another array directly, and yeah, it just works. You can also use Boolean vectors to do the indexing. So this one works also if you have kind of a Boolean index, but it also works if you just have an array, a vector of integers, which name the rows which you want. And this is what happens here, and you see the output is something quite special. So we have a lot of information here, and yeah, this is a special struct, a special data type, and yeah, actually we can check. This is from the distributions package on the distribution. So instead of what you may expect, we don't have a single prediction here, but actually we get a probability distribution back. So this is just how the package is implemented, because it has more information. So we get not only a prediction, but we get a whole distribution. And because this happens quite often, so this is one of the features of this package, that it really works seamlessly also with probabilistic models. It's good to see that you can now work on these distributions with just normal functions. So the distributions package itself provides a couple of functions how to work on this. And the mode is now, I guess, the most decisive here. So it gets the most probable value. And yeah, and this is Virginica in all our examples. So that's, of course, a little bit boring indeed. Yeah. I hope you have a bit better shuffling, or maybe no. This is really boring. Let's take another look. Maybe the first are better. Yeah, if I take the first 3, actually, you can see that things actually work. So yeah, so we now have kind of we can inspect the distribution. Yeah, we see that Cetos has 0, And where there's a 1, there's kind of full probability mass on this value. And we can also replicate it here by getting the mode. So it's a little bit more interesting. And yeah, and we can also compute some measures. And here, for example, the log loss, cross entropy also named. And we can average it. So this is element-wise operation, and we can average it. And we dictate our predictions and compare it with our original target values, but again, only the test subset. And this works because this is just a vector. So this was no table, but just a vector. Hence, we wrote it in smaller letters. Thank you also, Jerry, for answering on the chat. It's really appreciated if you help each other's, simplifies everything and makes for a great community. Thank you so much. Okay, so here comes the measures overview. Just that you know, this log loss is really just one of many measures you can use. So this is, yeah, all the measures there are. So 59 different measurements you can take. And yeah, and this is just an array, so you can actually look through it. And just that you have an understanding how this is meant. So there's a class here, so which has a couple of instances. So you can think of them as aliases to this class. And yeah, and our log loss is also in the instances. So it's one of these aliases, and we can display it to really see what it is. And every of this measurements, which is defined here, has a couple of more information which you can inspect. So our log loss has really our log loss and cross entropy as the alias names, and has the human name, a couple of more. What is interesting is that it has a prediction type. It's probabilistic, so you can also find this information in here. It has a default aggregation, yeah, and a lot of stuff. So that's really nice to see this overview, so you can easily inspect what is there. And yeah, I hope this gives you a better feeling, like, okay, the package is really helping you to find what all is available in this MLJ glue package. Okay, so the next, no, it's actually already the last part of this little supervised section, is that there's also an evaluate function, which is now combining fit and predict under the hood, and yeah, gives you directly an evaluation. So this is kind of the function which you're in the end are mostly interested in if you just want to compare models. So we again construct here our machine, and we haven't, yeah, and now, so this is kind of added in again, because so to really make sure that this is now doing things from scratch, yeah. So this is really doing all the things which we did above in one go. And yeah, so we have now our machine as the first argument. We can provide a resampling strategy. So there are many there. You can cross-validation. Here there's a holdout, which captures our train and test split. And we again have a shuffle false. And yeah, and we specify our measures. Now here we have our log loss, and in addition we have another measure. Yeah, Breer score. Sorry if not pronouncing well. And we have a repository parameter to get more information if we want. So you see that we get this, and it's really handy method you want to use. It just summarizes what we just did. Okay, so what you can do with this, you can also change information of your model. So we constructed the default tree. You can actually take a look at it. And now we just change. So the tree which we have looked like this. So we have a max depth of -1, so unlimited, and we now limit it to 3. And we can just do this and re-evaluate everything. And yeah, and I just to show you now made this probabilistic model into a deterministic one. So we can do this. That's really nice. And we now use accuracy and balance accuracy as example measures of this. And the key difference is now that I have this operation, which I specified to predict mode. And remember, mode was really the function from the distributions package. So this gets the most probable value and returns it. So that's a nice handy operation which you can use to just if you have a probabilistic model and but you need to plug in a deterministic version, that's super easy to do. And yeah, we can do this and we see that it also works. So downside of showing you both things at once is that you can't see that the probability is changed. So if you go back to these measures here, if you change them and take the operations parameter out again, we see that things changed. And yeah, actually our measurement improved. Wait, does it improve log loss? Yeah. Yeah, so last part here is that I want to show you that there are also the standard methods for unsupervised models. It's very similar. You fit them again, but they don't, you can again provide further data information here. And then they have transform, and some of them also have an inverse transform function. So it's really, you can think of unsupervised models in general of switching just the space. And this is kind of here also similar, like transform and inverse transform. And we will come back to them. So this is actually really by design to have these two functions that you can use kind of both versions on the same machine. And you just pass around the machines. And then, you can just call whatever way you want. And we will see it later on how we have time for that. Can evaluate take multiple models at the same time? No, actually not. So I also looked for the current state preparation of this little introduction to you, what there is for model comparison. And I unfortunately haven't found anything super fancy so far. So the simplest thing which you find if you search it, is just to compare them by simple loops. Just do the loop yourself. It's not super fancy, and then calculate all the measures. So that's actually a really straightforward way to do it. I hope I overlooked some result. I can take a look also afterwards and post some nice comparison helpers for you. But so far, my recommendation would be just to store your models in a vector and evaluate all of them separately by calling them by broadcasting this function or calling a loop. And that's quite simple. So you find, if you want to plot things, you find a couple of examples actually in the documentation and in example sections, and I give you the link on the bottom. So if you want to have some helpers here, there are some which you can just copy and paste. And I hope also that this kind of auto machine learning part is evolving a bit more. They have it on their roadmap. And I hope this is really getting more and more user-friendly so that you really just have to click on one function and things get compared. So I executed this and be coming there. So this was the very simple introduction so that you have a feeling that this is really just scikit-learn or what you're used to. So we saw the fit function, which let's start first. So we saw our machine, and this is actually the one extra thing which you probably haven't seen before. So we have an extra wrapper which takes our model, in this case the tree model, and our data and wraps it into a little meta representation, a little representation which just says, okay, this is our model, this is our learnable part of the system, and it needs the model, of course, and all this data, and then it can learn itself. And the learn parameter are also stored within this machine. So a learnable component, this is a machine in the MLJ context. And then we saw that we can fit such a learnable component. We can call the predict, we can call transform, inverse transform. And actually somewhere in between, we also saw that we have this predict mode. So that's actually also nice to see. We saw it in the measures. So when switching to the concrete measures, you saw that we have kind of this predict mode, and going a little bit to the top. So we have this predict, we can also directly call predict mode here. And then we don't get a distribution, but we get the mode, the single result, the most probable value. So we have a couple of these functions, these operations they are called on our machines. And they are kind of standard names. And one of the neat things is that you can actually really seamlessly combine probabilistic models with deterministic models. So this part is also one of the features of MLJ. Okay, so let's take a look on what MLJ says, what they really want to do. So they have a couple of features they speak about. So they really want to build a common interface for all the algorithms for selecting, tuning, evaluating, composing, and comparing machine learning models. So also this auto machine learning part really fits into their vision, their goal, and they're going to expand it in the future. And so they focus on Julia, but actually they write that they also would consider expanding to other languages. I'm not sure what the current state is there. So one part is that MLJ actually wraps a lot of scikit-learn models. So a couple of these models which you can access here are written in Python and accessed via foreign function interfaces from Julia. But there are also many direct Julia machine learning models. So they want to be data agnostic. They do this actually by having by supporting a tables interface. This is just a general interface for tables. You can pipe in data frames. You can pipe in distributed data frames. You can pipe in just arrays of named tuples. There are many different things you can use as the tables, and it will just work because what is used is not a concrete table, but really only a well-defined number of methods, and they are defined in this tables.jl package. They have really good support for model composition. This is what we're going to look into next. They provide nice syntax for tuning and evaluating models. We saw the evaluating part already. The tuning part I haven't shown. I'm not going to show you, I think. So this is really nice. They provided another wrapper tune model with which you can really just wrap your model and say, this and this parameter should please be auto-tuned. And then you have a new model which you can use just like the previous one and plug and play everywhere else. So tuning a model is really just like another model wrapper, which makes it really simple for the composition part. Okay, I already told you this. They have the consistent interface to handle probabilistic predictions. That's really one of their key focus points. And and here they again mention the tuning interface. And this works actually quite nice. They also have a paper where they present the key ideas again. Take a look at this. It's really nice. Really simple to understand. So not a fancy paper. This is a software open resources paper. This SOSS conference journal, I mean. So it's really made to be simply and concise, so everyone can understand this despite it's a paper. And then one final part to get this introduction done is that I really would like to show you that this MLJ comes with support for finding the right models. So this is a good part for the auto ML part, but you need to write a bit more around it, but still nice to see. So you have this models function. Remember we had this measures function. This is here now quite similar, just for the models. And you can call it without an argument. Then you see all the models available. And here we provide another little argument. This is a matching. And we provide the X and the Y. And and we see all the models which can actually work with our data, which we just used. And that's really nice to see. So we have 47 models which could handle the data which we used. And we now could just loop them and try them out. So the AutoML is really not far away here. And I was myself surprised that I haven't found a good summary for that. Sure, it's not far away, but doing it programmatically, that's, I myself was surprised by this. We have a remark by CM. Thanks for asking the question. So matching documentation is unfortunately empty. This could be improved, definitely. However, there is some documentation for it, and this is in the models. So apparently you only use matching in the models. And yeah, I actually execute this right below. And there you have the information. So list all models for which the filter is true. And so the matching is constructing a filter. So it does not execute anything, but this is, let's take a look. So this is really giving you a little helper tool. Yeah, it's called a checker. And here you can parse in a model. Yeah, let's do this right away. So we have now all the models. Sorry, it's not possible. We get failure after loading all models. But yeah, so this is kind of an interesting part. So I hope this will be much faster the second time I run it. This is now combining. Yeah, I need one. Yeah, so we can give it a model and it will put false or true. And yeah, let's see another one. Yeah, so this one is actually matching. So this is the whole thing. Yeah, this matching constructs a little function, which is then used as a filter. I hope this answers the question. And I agree that someone could add a docstring to the matching function. Okay, so still super nice to see. I'll delete it here again because I have it here below. So I wanted to show you this. The documentation of the models is the one which you would like to look a bit more into it. Yeah, so CM, I hope this answered your question. Yeah, so we can more or less only use it within the models function. And maybe let's see also all the models. So just to have a look over them. So there are currently 169 models. We have another question. Thanks for all your participation. It's really nice. Matthias asks, Matthias Villani, a lot of models come from scikit-learn. Indeed. Is that a Julia port of the Python package or just Py calling into the Python scikit-learn? That's a good question. So indeed, so I was assuming this is, now I bet this is using the scikit-learn package. And I haven't installed it yet, I guess. So this is, yeah, an internal dependency. So we could add it, but it's a well-known package. And looking into it, so usually you can search for Julia packages super easy. You type the name and press a .jl in the end. And this will directly give you the Julia version of whatever package this is. So even if something is called scikit-learn, that's really nice. And this is the package under the hood. Yeah, and it implements the scikit-learn interface and algorithms in Julia. It supports both models from Julia ecosystem and those of scikit-learn library, and it uses indeed PyCall under the hood. Okay, I'm a bit slow here. I'm getting a lot of okay, so I hope this answered your question. My system is apparently yeah, having problems streaming and doing some things here on the browser. Yeah, so it's a mixture. Yeah, so last thing I want to show that you also have a lot of information about. Yeah, okay, yeah, just yeah, the matching part. Yeah, okay, thanks CM for. If you have time more, we can take. You can stay afterwards a bit longer, and I can explain more details. I think for now I'm going on, and thanks also for mentioning that it's fine so far. So there's the info command, which you can also use for the single models. So now we have this decision tree classifier, and again we need to provide the concrete part where it is in, and we have then some extra information like we had it for the measures. And I just want to show you this in case you're searching for that. So yeah, there's a lot of extra information which is here, and there's also again the prediction type. It's probabilistic, and many other things as you see. But yeah, it's good to know that there's one place where all these is aggregated. Okay, so that was the first part, and we have kind of 45 minutes used so far, and now I would like to go into a little more advanced example, which shows you how you can compose models into a bigger model, which you then actually can reuse again as a part of something even bigger. So yeah. But yeah, let's halt here for a moment. So are there some further questions to the part so far? So we've really seen kind of standard fit, predict logic, evaluate logic. Okay. Great, then I'll go on. So let's take a look. This example now is actually, more or less completely. I adapted a couple of things taken from MLJ. So also previously I already told I plugged together a couple of things from MLJ, but the first part was really a bit more like from multiple places, and this is more from one place now, or like two places. And yeah, so also with a bit more text, which I copied just from the original one. So what we are now going to look in is how to compose things, how to compose little machine learning models. And these have a special name in MLJ, and they're called learning networks. So on the first glance, this may be a bit, may think of a neural network. That's not a neural network. That's really probably the idea is similar. So we have a network of things, like you see here below in our little graph. It's really like that's the idea. We call this graph now a network, and it's a learning network because of our original machine idea. So this is really standardized here. This network can consist of some static parts, some just functions which do some computations, and some learning parts, which are just our machines. And this idea also now they used to give them this name. They call it learning network. Okay, so what we want to do is this little model, which you can see here in this nice graph. So we have some input data X, and we have a target variable Y, just similar to what we did just now. Then we apply a standardizer to our X, which gets us a W intermediate representation. Then we do a box cox on our Y, which gets us the intermediate representation Z. And this one is actually invertible. So this is an unsupervised model, the box cox, and the standardizer is a supervised model. And in the unsupervised, we saw that there was also this inverse transform. And we use this to come back from our internal space into Y. And this is really already depicting one of the ideas which are behind MLJ. So usually you can also do this inverse by just grabbing kind of parameters in here and inverting them. Like an extra step. But in MLJ, this is really, to my understanding, well abstracted. So you call this inverse function on the very same machine, and you reuse kind of the reference. And this makes for a really clear dependency graph. So what they depicted here with the dashed arrow, this is really the core idea, or one of the core ideas behind MLJ, that they track these dependencies in a rigorous manner. We combine our supervised model with our unsupervised model here in the intermediate space, in the latent space with the rich regressor, and get our target, so our prediction on the intermediate space. And this we invert. So sorry for confusing. So this the standardizer is not the supervised model. I was confusing myself. The standardizer is also only an unsupervised model. So it's whitening the data, and then the rich model is our supervised model. And so it gets our covariates, our data, and our target variable. So the rich is our supervised model. And Okay, so let's take a look into how we really do this. And yeah, so a bit more text here, just because I wanted to account for the original author, so they put it in there, so I want to leave it. But the key note here is that we now have a little wrapper, which is called source. We'll see this in a minute. And we otherwise than this really do the same like we did just now. Yeah, they call it here, we do the various steps by hand. So the basic idea is to proceed as if one were composing the various steps by hand, as we've just done it, but to wrap the training data, so the input data, in source nodes first. And let's see, let's take a look at the code, how this looks like. So here we have our input layers, and we construct them by a little helper function, which is make regression. And yeah, it's just synthesizing some training data for us. And we take the absolute value of our y. So this is just an example taken from MLJ tutorial. We again have our partition function. You already know that. We have now an 80-20 split. And yeah, and now comes the new part. And this is our source command. So yeah, let's run this. And let's also take a look at what the source did. So we have now an XS and YS, which are no longer plain values, but they're wrapped into a node. And yeah, we saw that the YS is already printed. So let's take a look at what this is. And yeah, so you will, it's even a source and should have a super type abstract node. Yeah, so this is the name which MLJ uses here for this graph representation. So it's really now one of the parts of this graph. Yeah, so we have now it made into this first part. So it's, yeah, hence the term node. Okay, so these nodes are actually just very small wrappers around it. So if we just look at it, we get the source, yeah, but we can directly call a node always to execute it. And here we see then our original y value. So this is really the same. So all the elements are actually really identical. Okay, so that was our input. So now we do this first layer. So we have the standardizer, which we apply on our X, and we have the box-cox transformer, which we learn on our target values. Okay, so we again see that we first construct the model, yeah, which is just calling our constructor, and we wrap it into this learnable part of which is called a machine. So this is then getting all the parts which it needs for learning, namely the model itself and the data. And the same goes for the box-cox transformer. Again, we wrap it into a machine. So, and here now they are both unsupervised models. We call the transform function. So here we use the explicit syntax. Actually, we don't need this. We could also just call them them. The tutorial here made the explicit version, which is actually, if you build more complex stuff, it's a good idea to use explicit style. But yeah, this lazy version without it is also quite commonly used. So it depends a little bit on your taste, but don't be afraid of writing a couple of letters more. So this is really nice style as well. Yeah, so this is now a new node. Yeah, so we have first a model, then we have our machine, and then we have this little output of our machine, the transform function, which then is again a node of our graph. Okay, so these we can combine further, and here comes the supervised part, so the rich regressor. And yeah, we provide one of these parameters from one of the hyperparameters, and again put it into a machine. So that it's supervised, so we have the dependency on the standardized input data and also our latent space Z. And yeah, and here actually we do the same. That's interesting. So This is even a bit more complex than the little graph I showed you above. So the tutorial was expanded to actually include another supervised model here next to it and combine them. So one step further, but nothing super complicated. You see that we have a second supervised model. And again, we have the machine. And now we construct our target prediction of the latent space, Z hat, with a 50-50. So we use 50% the prediction from our rich regressor and 50% the prediction of our forest. And yeah, and we provided the data explicitly now. So yeah, so I think this actually this is not needed. Let's execute this. If I execute the one above, no, I forgot. Okay, so yeah, regressor is not defined. I jumped about a couple of things which I should have executed. Yeah. So I bet you did things a bit better. So here I allowed the models, rich regressor and random forest regressor. This is actually a good hint. So here the behavior changed in a recent version. So the loud macro previously directly stored the rich regressor to rich regressor itself. So hence you may find a couple of tutorials which still use this old implicit variable assignment. This is gone by now, and you need to explicitly assign it to a variable. So easy to do, yeah, but still you need to know it, and so that you don't wonder why things don't work. And yeah, so now we have these available, and let's re-execute things. Nice thing about Julia, it's yeah, just in time compiled, just ahead of time compiled, and so second execution, when now nothing has to be compiled again, second execution is super fast always. First execution might be a bit slower, as you probably know. Okay, so now we have our combined model. Yeah, this here even a combination of both, so you can play with it a bit more. And you see that this is also a node. Yeah, so this is kind of really interesting to see, and I think this is why they expanded this example. So they multiplied by a scalar, by a simple value, and they also added 2 nodes. And all these operations, they are overloaded to also work on nodes. So nothing is really executed here. It's really just a graph representation, but you can use the standard syntax because Julia allows for defining all these operators for whatever you want. So that's nice. And yeah, and final step is that we invert our latent space and we get, again, a nice representation. That's, yeah, I find this really lovely made so that you have a good understanding of your model by just looking at the output. And yeah, and now nothing has been done. As said, okay, I have a nice question from Matthias, Matthias Villani. Thanks so much. Actually, we haven't learned anything so far. So this was really only combining all the parts together. So we just stacked up our composed model. And this is now the step where we learn it. And MLJ knows all the dependencies because, yeah, this is kind of its job. And we can fit our predicted target value and does it. And then we can also look at our predicted target value because our input sources actually wrapped real data. So this is also, we don't need to provide any extra data. We just use the fallback data from our sources. And yeah, this works. And you can also fit anything in between and it will understand what are the dependencies. So this is really the idea of this learning network. It knows which part of the network needs to be learned and still has the dependencies and just, will train all the parts which are needed. All the dependencies of your node will be trained before your node is trained. So, and this works. So we have now our prediction. So I hope this was straightforward, and at least it was for me. And now there comes a nice little extra. This was kind of the by hand part. So we really did everything like we would have done it in an interactive mode. And now there comes a little nice macro again, which supports to write this into a new type, a new model type. So it's a bit more complex, but it's really nothing fancy. So we have let's start with init. So we have here a little mutable struct. So this is standard Julia. Yeah. So if we run this with a different name, it's important to have a different name. You see that this actually works. This doesn't work. Okay, sorry. Of course, this doesn't work because there's this default syntax. Default syntax does not work directly. This is kind of the idea. And now you have the test composite model, which you can fill with stuff. So 1 and a 2, yeah, and then you can access the components again. So this is the syntax that really exists in Julia, and this is just reused here for better understanding. And yeah, we write the first component then to we point to our rich model, and the second component to our forest model. So we are missing the Cox model here. You can kind of change this and see what it does. And so this is kind of the part where we reference our components. Yeah, so this is really flexible to you. You can give your components the names what you want, and then access all the hyperparameters by going through the different fields. And then we need another part here, which I skipped so far. This is then, a specification of our composite model. So this is again a machine, so a learnable component. You could use this somewhere else in another composite model again, and it needs to be specified at least in some terms. So here there's a kind of, I would call it a dummy model. There's deterministic, there's probabilistic. I think there's something more. They call it a surrogate, which really just says which model class is your composed model. And yeah, so we reuse this field in a little different manner, but it really makes for an intuitive feeling. So we now have a deterministic model, not a probabilistic one, a deterministic one. We get our input data again, so our x and our target variable y, and we can specify our output operations. So we have the predict. You remember the general predict, and we could also add others here. So, but the predict is now the most important for a deterministic model. If you have a probabilistic model, then predict would return the distributions, and there was, remember, the predict mode, and you can point it to just another one. So in this case, then distributions.mode von y head. Sorry, I'm a bit slow with writing this head. So that's really the same simple idea. It's just referring to the node which we executed, and this little macro here, this does all the magic of then combining it to valid representation. And this is really now stuff which you can reuse. So this is now something, you can put this now in the package and others can really use this model. So super nice. And we can also create it ourselves and see all this nested hyperparameters. So lovely. We have the regressor 1 and we have the regressor 2, and we see all the parameters. And yeah, as you would think, we can also access them and change them. So this thing is mutable, as the command suggested, and we can change our lambda and investigate it and then re-evaluate stuff. Yeah, and this brings me here to the last cell actually. So this, we will look into more tutorials, but this is now ending the little advanced section. So you can also evaluate this composite model. And there's now there's another version of this evaluate. Remember, before we used evaluate with an exclamation mark. You can check it easily by going back to the code. And it got a machine. And the machine was already bound to the data. And here we just have the model part. And there's another version, this evaluate, function which can evaluate the model itself, but you need to provide the data in addition. So other than that, everything is the same. Yeah, there's the resampling and the measures. And now we have another resampling strategy, a cross-validation, and we can do this directly and check. And you can now mutate the hyperparameters, investigate what it does, and this part works. So it computes a bit more. First time it always takes a bit more time. So we load here some example data, the Boston data, and just apply it to it. Yeah, second time is then always much faster. Okay, we get some live feedback for evaluating, so it really was compiling stuff, and we can re-evaluate it, and it's much faster. Yeah, and you can now also again kind of change the parameter. So we have the registered 2, and we have the max depth, which was previously a -1. We change it to 3 again, and we can evaluate again. Oh, sorry for I should put it somewhere else and re-execute this. So we should see slight differences. Yeah. Okay, so here our error actually increased by restricting the depth, so we get no generalization benefit. Yeah. But of course, this is also only a point. So to make better evaluations, we should maybe add some probabilities. Wow, so nice. Thank you so much for opening the pull request. This little N really, really loved. That's totally nice. Thank you so much. So this was the advanced part. And are there some further questions here? What's needed to use your own algorithm with an MLJ? Question from Jens Bruno Wittek. Thank you so much. Actually not much. So we've seen this part that you can kind of compose things yourself. So the static part is kind of very simple. Combining stuff with static functions, you can directly use them. And if you have another learning part, that's a good question. You should look into the wrapping of one of these packages. So if you have the decision tree, take a look at the wrapping they did there. I actually haven't so far, but it should also be. So this should be super simple. I'm a bit slow on performance here. So the MLJ documentation provides you with a lot of information. So this is well-documented package. And one of the generic wrappers, which is really maybe what you could use here, is what they call an iterated model. So where you have several steps, which then finally will get to your final step. And take a look at this. I'm now struggling with my computer. Hasn't happened before so much. I'm a bit surprised that Chrome is not responding. Let me switch to Firefox. No, it's my Windows Manager. Okay, I hope it's coming back. Can you still hear me? Give me some feedback. Just curious.
Yeah, we can hear you, but we cannot see
you. So I hope the operating system is back in a few minutes. So the iterated model, this is really the way to go. That might be the simplest way to wrap your model into something which MLJ can understand. This was originally developed for deep learning packages, but it's far more general. So if you imagine kind of a workflow like you have You optimize for a parameter until it kind of meets a threshold, yeah, and you do this iteratively. Then you can directly wrap this method into an iterated model, and yeah, it gets kind of a good support for the MLJ package. Yeah, thank you so far. Yeah, so this is really unique. First time it happens that my operating system freezes, but it's really nice that people can still hear me. Yeah, that's lovely. Some other questions. So I actually can even see updates. Yeah, so it's impressive. So bye, Helmut. Yeah, thanks for being there. Other questions? Okay, so despite I can't show it to you now, at the bottom of the Jupyter notebook, you find a couple of links. And yeah, and the last part of the interactive part itself is mentioning the tutorials. So there are a couple of tutorials, which unfortunately I can't show you now, but you see it themselves. They are not Jupyter notebooks, but still kind of similar, like more in Markdown style. You can just copy and paste them into this Jupyter notebook, which you just have, and experiment with them a bit more. So they provide really a bunch of examples where you can go into more depth. Also, take a look at the tuning part, which we haven't went into details. It's just nice to see that you can use hyperparameter tuning just as another layer of your model composition. So this is really nice part of the MLJ. Yeah, and then they wrote 2 papers, check them out, and they also have super documentation. And in case you have some other further questions, always feel welcome to also reach out to myself.